Good afternoon. So this is the first lecture of geometry. So these are all the topics we are going to touch in this course. In this first part, we will touch 5 of them, and then the second day we will go through the rest. So today we are going to see have an introduction of what are the physical volumes available in Geom 4. We will touch on touchables, different kind of parameterization, include the nested parameterizations. We will see how to create divided volumes, assemble together volumes, and reflect volumes. So I assume that some of you have already participated to the first course, or in any case are a bit familiar on how to build a simple geometry, a simple setup, basically composed by placed volumes. So you are a bit knowledgeable about the meaning of these three layers that exist: solid, logical volume, and physical volume. Okay. So the logical volume is an important part because it is the class that groups together all the attributes that are common to all volumes you want to place in your geometry that have that characteristics. The physical volumes are by far the volumes that are placed in the space, so they bring together position and rotation in the space. So today we are going to see basically different kinds of physical volumes that exist as placed volumes and then as replica or parameterized volumes. So placed volume is conceptually is a volume that is placed in the space, and it corresponds to one only position volume. So it means that every time you create a placed volume, the class G4 PV placement, you create an object in memory that represents that volume in that specific position. The other concept is a repeated volume, so an object that represents many volumes placed in different parts of your detector as a single object. Okay. What is the difference? What is the advantage of having this kind of representation? With repeated volumes, you can represent many volumes with a single object. So in the end, you are optimizing memory consumption. So you reduce memory consumption. So it is especially useful for applications where you have a repetition of many volumes of the same kind that share the same material in the space, or that are parameterized along some characteristics. So repeated volumes can be either parameterized, and the parameterization can apply to different kind of situation, can apply to the size, to the positioning, to the material, also to the shape, or can be simple replica or division. Replica division are simple repetition of that volume along a certain axis. It is important to know that a mother volume can contain either many placed volume or a single replicated volume. So replicas are represented by the class G4 PV replica. Is written here, that I said are represented daughters of the same shape aligned along one axis, and as the characteristics that the daughters, so the slicing, I mean the division of these daughters of this volume fills completely the mother volume of the replica. Okay, so there are no gaps between the daughters. Divisions instead are kind of replica where you can have a gap between the daughters and the mother volume. We will also see today two kind of structure, special structure, that are called the reflection factory and assembly volume, that allows you to reflect a complete trio of volumes, or bring together, group together a set of volumes that then you can position in space several times. So let's start with the simple replica. So as I mentioned before, a replica, the characteristic of the replica is that the daughters that compose the slicing of the volume must fill completely the mother volume. So like in this case, you have a mother volume which is a parallelepiped that gets filled by many layers, and they all fill completely the parallelepiped. So the replication can happen, can occur along certain axes, depending also on the topology of the volume that gets sliced. So if it is the case like a box or a trap, this is the Cartesian axis, and the coordinate system is at the center of each replica. On a tube, a cone can be on the radial axis, where the coordinate is the same as the mother, and also on the phi. So when you have sections or wedges of cone tube, in this case, the coordinate system is rotated such that the x-axis bisects the angle of by each wedge. We will see this later. So this is the constructor of a PV replica. So you have essentially as argument the name of the volume, the pointer to the logical volume of the slice, the pointer to the logical volume of the mother. Then you must specify the axis of replication, the number of replicas, the width of the replica, and optionally an offset, which is a distance from the mother replica. And the offset can only be used for tube and cone segments, and we will see later why. So some feature restrictions that you have to take into account is that you can have replicas placed inside other replicas, so this is possible, as long as you respect the concept of replica, so that it fills completely the mother volume. Normal placement can be placed inside the replica, assuming that you do it correctly, so you don't cause intersections, overlaps with either daughters or the mother. And no volume instead can be placed inside a radial replication. This is mainly for the complexity of the representation of a radial replication, which is difficult to handle for the case of overlaps that may be generated. And then simple parameterized volume cannot be placed inside the replica. So these are constraints that apply on when you create a replica. So these are the three kinds of replications according to the different axes. And you can see for the case of the Cartesian axis that the center of each slice is given by this formula. And in this case, you don't have possibility to use offsets. While for the other two, replication in rho and phi, the offset determines the distance of the from the original mother volume, not sliced. So in the case of rho, the offset is the inner radius of the mother. In the case of phi, the offset must be the starting angle of the mother. So when you define the wedge, it is the starting angle. Okay, parameterizations. So parameterizations are kind of replicas, but they are special in the sense that the replication of the slice are computed based on a formula. So this formula, the parameterization formula, is something that is provided by you. So it's the user that has to define the parameterization. And by doing that, you have to implement a concrete class, a class that inherits from G4 VPV parameterization and define the kind of parameterization that you want to apply to the to your solid. The parameterization can happen in different way. So it can be done on the size of the shape, on the material, on the positioning, also the visualization attributes, and also the shape, the kind of shape. And it is a formula that is based on the use of the copy number of the slices that somehow index the parameterization. It is again a kind of construct that is important in situations where you want to reduce as much as possible the memory consumption. So you can imagine, for example, the implementation of a phantom in medical physics, where you have a tank which is made of water and is a model that has many cubes. So you can have millions of these cubes. So they have all the same shape. They are simply positioned in different places, and they are parameterized according to material that you may have. So in that case, you don't want to define each single volume for each cell, but you want to create a parameterization that eventually reduces this amount of volumes to create. So those two parameterized volumes are allowed only if the volumes are identical in size and shape to the mother. Parameterization of composed solids like Boolean, reflected, or displaced solid are not recommended, are not supported, given the complexity that this may imply. And one thing that we will see in the next lecture is also that the parameterization support a different kind of parameterization that we call nested parameterization for special cases that we will see. And it is used in the same way as a normal parameterization. So how we parameterize a physical volume. So as I said, the parameterization is defined by you, that defines the algorithm that implements the parameterization scheme. So this is done by inheriting from a class G4 VPV parameterization, which is an abstract class. And you have to define then the parameterization as a function of the copy number. So essentially, this copy number will represent, for example, the positioning of the shape. So it can be the translation and rotation. Can represent the size of the shape. So you can have a parameterization that parameterizes the size of the solid, or the material, the sensitivity, the visualization attributes. So all daughters must be fully contained in the mother. So you must avoid situations where they either overlap each other or they may protrude from the mother volume. There are some limitations that apply because parameterization apply only to a limited set of solids. So you have here a list of solids where you can apply parameterizations. Not all solids that define Gen4 can be parameterized. It's a rather wide set, but they are not all. So you have to take this into account. And one important thing to consider is that it is always good to have the parameterized volumes to be as the last in the last leaf in your tree of volumes, so that you can control better, when a particle enter into a specific copy of your parameterization, you can know exactly which this copy it is. So, as I say, typical use case are complex detector with the large repetition of volumes, regular or irregular, and in case of medical applications, as I was mentioning before. So this is the constructor for G4 PV parameterized. As for the replica, it has a name, the pointer to the logical volume of the parameterized entity, pointer to the logical volume of the mother. Then there is an axis, which in this case it is not the axis of replication, or it is simply a hint that you give to the system to identify if there is a pattern in your parameterization for optimization. So for example, if you do parameterization by location, which is mainly a placement along the x-axis, you can specify the x-axis, and by doing that, the system will then apply an optimization which is only related to the x-axis, and this will reduce the number of voxels that are generated in the optimization system for creating the 3D parameterization. This is, of course, not mandatory, in the sense that if you are not sure what hint to give, you can simply put a key undefined, and in this case, the system will, by default, apply a three-dimensional optimization. Okay. So you have then the number of replicas, which is the number of times that that you want to parameterize, and then the pointer to the parameterization algorithm, that is the one that defines your parameterization. There is then an optional argument, which is a flag, a Boolean flag, that if you set it on, it will enable the overlaps check at the time you create the parameterization. Okay, so this is useful, especially at the beginning when you are implementing your parameterization, to verify that you do it correctly. So once you see that you don't have overlaps, then you can leave it to false, and that will be faster. Okay, so now let's have a quick look to one concept, the concept of touchable in Gen4, which is as important also for the kind of analysis you may do as a post-processing or during tracking, and is important also for the next concept of parameterization that we will explain. So you know that a track in Gen4 is composed by steps, and the class that represents a step in Gen4 is a G4 step. G4 step has two step points, which is the start step point and the end point, which is pre-step point and post-step point. Okay. What you have to know is that all the geometrical information of a particular step is always good to take from the pre-step point, because it's the point you are sure that your particle is in exactly at that moment, and that will tell you from where the particle at that point goes. Of course, you cannot know in the post-step point where your particle will be after, because it may exit a volume, will be in another volume. So this information of the pre-step point may be lost at that time. So it's always good to start from the pre-step point. Each step point provides the position in the world coordinate system, global and local time, the material that applies to the volume where the particle is placed, and a handle which is called the touchable history, which is the one that gives you all the rest of information of the geometry that you may need of. So the touchable history is like a vector of information of each geometrical hierarchy. It includes the copy number, it includes the transformation, rotation on the mother of the volume, and it is accessed through handle or smart pointers. The touchables are special objects that are reference counted. Okay, so a touchable always is I mean, you may have many physical volumes in your geometry, but you know that the physical volumes may be, you know, replica of different volumes. You may not know if they are real entities or if they are replica. And the touchables guarantee you a uniqueness of the volume, of the physical volume you are in your geometry. So it is always good that when you want to know where you are, that you talk with touchables. So here is an example for example, of what, and these are things that you will use a lot. So a touchable history has the information of the geometrical hierarchy. So you have like in this case, some point you have a step, a G4 step, and from the step you can retrieve the step point, in this case the pre-step point, and then from the pre-step point you get the touchable, okay, which is a touchable history. The touchable will give you access to the volume where you are and to the copy number. So that is a copy number of the place where your point is in that exact moment. You can get with the same interface and increasing the index in get volume, you can have the mother copy number or the grandmother copy number if you go up. You can retrieve from the pre-step point the position in word coordinates, and you can convert this position by accessing the touchable and getting the transformation, passing the point to the transformation. And this will give you back the local coordinates of the point. So these are important things that you will use either in your step in action or in your code where you want to know where you are during the simulation. So now, in coming back to parameterizations, one particular construct that Gen4 provides is a possibility to nest together parameterizations. So suppose you have a geometry with, like I said before, a three-dimensional regular repetition of boxes of the same shape and size, and you have a material map of such volume that change according to the position, so like in a phantom. So it may come natural at first to create a three-dimensional parameterization of this kind. Okay, so you simply parameterize the position of these cubes in 3 dimensions, and you create as many cubes until you fill the full matter volume. However, this is not efficient. Why is not efficient? Because you will, in any case, create in a single parameterization, you may create millions of these things. So what is good to do instead is to proceed like this. So you create first a replica of layers in 1 dimension. Then in a second axis, you create another replication. And in the third axis at this point, you create a parameterization that fills up the layer. Okay. So the advantage of having this is that you will have much less memory required for the geometry optimization, and you have much faster navigation for very large number of voxels. Okay. So you have 2 levels of replicas, and then the last level is a parameterization. Okay. So to help in this, there is a concept in Gen4, which is this nested parameterization, so that you create 2 sequential level of replicas and then 1-dimensional parameterization. And the material of a single voxel is parameterized not only as the copy number of the voxel, but also according to the copy numbers of the ancestors, because that's the only way you can really identify exactly which cell it is. So the material is indexed as 3 indices, okay, in the 3 dimension. So the class G4V nested parameterization is a special parameterization class that derives from G4 PV parameterization and is specialized on this kind of construct because it provides you a method that you will have to implement, compute material, which provides as a pointer access to the touchable object of the parent physical volume. Okay. In addition to the copy number of the voxel that you have to use to implement your parameterizations. And this will help you to determine the indexes of the parent volumes. So in this case, you will have from the touchable, you will able to get what? To get the copy number of the first axis, the copy number on the second axis, and the copy number that you know already of the volume of the parameterization itself. So these are essentially how it looks like. So essentially, you will have the usual methods that characterize a parameterization, like compute transformation, for example, that will determine where your volume is located. But one in particular, this compute material is the one that gives you access to the parent volume touchable. And then you have other two methods, utility methods like get number of materials, which will return you the total number of materials, and another get material that given an index returns you the exact material at that index. Okay. May I finish just the part, please? And, as I was mentioning before, the nested parameterization class is like a normal parameterization. So when you use that in a parameterized volume, it respects the same interface. So therefore, will not make any difference between the two. All the other arguments of parameterized are unaffected in a sense. So there are some limitation here. So for example, nested parameterization of a places volume are not allowed. So you are only allowed to do nested parameterizations if you have repeated volumes, like I was telling before, two levers or replicas, and then parameterization. You cannot have in between presence of places volumes or other kind of volumes that are not repeated. Okay.
Okay, the first question goes back a little bit, but daughters should not overlap each other. How are boundaries of objects handled? Can they touch, or does it have to be a non-zero gap of mother material between them? I have answered no. There can be the daughter volumes can touch.
Yeah.
The second question is regarded more parameterized volume, which is why I waited until now. But the question, the person asking says, as far as I know, normal G4 navigation with parameterized volumes is slow. Right now I'm using regular navigation. Is it the fastest option? What about voxel navigation? One of the things to clarify is that when you have more than a few daughters, more than a couple of daughters, even if you do not request it, voxels are created in Gen4, and that's the way that parameterized volumes are typically handled.
Let's say they are slow. It depends. I mean, the parameterization, the speed of a parameterization, a lot depends on the parameterization algorithm. So if your parameterization algorithm has some inefficiency, that you will pay quite heavily. So one has to make particular attention, especially in positioning when you start manipulating rotation matrices and this kind of thing, because every operation that you do in your parameterization will be computed every time you do a step, essentially, and you enter into that geometry.
I'm not sure if I put the context. The person is using medical CT DICOM images, so everything.
So in that case,
there's no rotation. And
in the case there is yeah, we are not touching that, but there are also other another system in Gen4 which is called regular navigation that is optimized for certain kind of DICOM images, because it allows you to skip, for example, materials boundaries when you have voxels with the same material, so you can, instead of making discrete steps along all cells, you can skip the boundaries that have the voxels that have the same material. So yes, there are some advantages in using the regular navigation.
And another question, which is for that specific question, but otherwise also, how do you choose? If you have multiple axes, do you choose just the longest axis, or otherwise, when you're talking about
the axis to suggest? Well, in that case, you can simply put k undefined. In that case, the system will take care to make the proper optimization.
Okay, that's. Oh, the final question has to do with visualization, but I don't think we're able to answer it right now. So we'll see if we can get an expert answer at some point.
Okay. I don't know if there are questions in the room, or if everything is clear. Okay. So now let's have a look at another kind of replication, which is divided volumes. The division in Gen4 is a special kind of parameterization. Actually, it is implemented as a special kind of parameterization, but it is a replica effectively, I mean, as a concept. Why it is done this way? You have that in this case, the volume gets divided, and the division itself gets automatically, the algorithm for making the division is automatically generated in Gen4, given the parameters that you give to the division object. So division is similar to a replica, with the difference that it can have gaps between the mother and the daughter volumes. As for replicas, it must obey to the rule that the shape of the daughter volumes must all be the same as of the mother volume. Okay, and the replication must be aligned along one axis. Of course, if you have with the divisions, you can also implement normal replicas, but it would be less efficient than normal replicas. So if you have a simple replica with all the slices that fill the mother, it is better if you use a replica and not a division, because it is more optimized for that. So that's what a division would look like, and you see, you define a gap, and then it will fill up until the number of replicas that you want. So there are different kind of ways to build a division, the different constructs. The first one is this. So all of them will have a name pointer to the daughter logical volume and pointer to the mother logical volume. Then they will have, in this case, the axis of replication, the number of divisions, and the initial offset that you want to define from the mother volume. Okay, I lost the cursor. Okay, so in this case, you see that you define the offset, and then the size of each daughter volume is calculated with this formula. And what will happen is that the system will then calculate automatically how many slices will go into your mother. The other construct foresee that you define the axis, you define the width of the slice, and the offset from the mother. And in this case, the number of daughter volume is calculated with this formula. And what happens is that you will have then this kind of representation. And when you reach the end of the mother volume, simply the last volume will not appear. Okay, so you will have another gap. The other construct is that you specify axis, number of slices, width, and offset. So, like, you limit the number, the area where you want to include your slices. In this case, you will have that the system will just do this. Okay, it's very simple. So these are all the supported cases for division. So the kind of division, the kind of axis that is used for division depends, of course, on the shape. So for solids of the kind of a box, TRD or para, is the Cartesian axis. For tubes, cones, polycone. For tubes and cones is the rho, phi, and z-axis. And for polycones, similarly, but with some caveats. But for the polycone, for example, when you parameterize along the z-axis, the number of divisions has to be the same of the solid sections. Okay, so the width in this case will not be taken into account. Same for the polyhedron. In addition, here, if you work to the phi axis, the number of divisions has to be the same as the solid size. Okay, so the width in this case in phi is not taken into account. Okay, there is also another special construct that you can use, which is called the replicated slice. It is like a division, but and there's a similarly three kind of constructor which are similar. But in addition, you can specify an half gap between daughters. Okay, so that allows you to specify essentially your divisions this way. So these are the slices, and those effectively get constructed, starts from your half gap, and then gets repeated in every single place. Okay, so it's very special construct, but sometimes very useful to have. The concept is exactly the same as the one for divisions. Okay, so now let's have a look on the special constructs. We start with the assemblies. So an assembly is when you should use an assembly? When you have a situation of a pattern of volumes that are repeated several times in a space, but may be difficult to implement each time or construct each time because I don't know, the volumes are somehow interconnected, they are rotated, interconnected. So in some sense, it is complicated and error prone for you to define every time all the different components of your structure. So the assembly allows you to define this group of volumes as a single entity, and then imprint them wherever is needed in a single go. Okay. So the structures that you define may consist of different shapes, may have volumes that are more or less dense in their location. They can be hard to define or describe as a simple replica or as parameterized volumes. So, like in this case, you see the assembly volume acts as a kind of envelope. So you define an envelope, and inside this envelope, you place the components of your assembly. And then once you make the imprint of this envelope in the space, the envelope disappears. Okay, so it's like it drops the volumes that composes the envelope are dropped as placements in space. Okay, so each one will be a single physical volume that is placed in space. So you have to be so careful in using this feature, because that means that you may put at the same level, so as daughters of the same mother, many volumes at the same level. Of course, if you talk about thousands and thousands of volumes, it's not a good thing to have, because you are sort of, let's say, having a flat structure that won't help then the optimization system in the way it will have to optimize the geometry. But in some cases, it can be very useful. So the components of an assembly are essentially a triplet, where you have a logical volume, the transformation versus the envelope, and the rotation eventually versus the envelope. So this triplet represent the daughter volumes that participate into the assembly. So here you have an example. So actually you see here the main function that belongs to the assembly volume, which is the one that defines the assembly. So you in this case is add placed volume is the function that adds into the assembly one component of the assembly. So you have a pointer to the logical volume, its translation and rotation relative to the envelope. Okay. So once you have applied this function as many times for creating your assembly, you can then make an imprint of the whole thing using the make imprint method. And once you do that, for each physical volume, the system will generate the name of the volume that finally gets into your geometry. And the formula that is used, the format that is used, is written here, where you have essentially represented the assembly volume instance number, the assembly volume imprint number, the name of the placed logical volume in the assembly, and the index associated logical volume. One thing that you have to know is that all volumes that are, let's say, part of an assembly volume are automatically handled by the system. So you don't have to worry about the destruction of the object again generated in memory, because the system will take care to create and to destroy these objects. So here an example. So we create an assembly volume, which we represent as an envelope. We define a rotation matrix, a translation, and then with the add placed volume, we add a volume to this envelope. It appears here. We do this for as many volumes that should be part of the assembly. Okay, we repeat this kind of operation, and then once we have done that, we can then imprint this assembly as many times, giving a rotation and a translation of the placement itself of the assembly. Okay. Fine. Yes.
The question was, can you have a hierarchy of assemblies? Can you create an assembly that includes assemblies?
Of course you can. And one thing that you have to take in consideration is also that every assembly you create, even if the envelope somehow disappears at the time you then make the imprint in your geometry, the assembly itself is stored in a special store. There is a for assembly store that contains and give you reference to all the assemblies that you have created. So if you need to go back to know in which assembly was created a special instance of your volumes, you can find into the assembly store.
One way to run out of memory would be to create an assembly with 2 volumes and add a third one to create 3 of them, create 4,
exactly.
4 of them.
Recursively.
Just a few of that, and you can probably run out of memory.
That's this is true for every volume, honestly. Okay, reflected volume. So another thing that is possible in Gen4 is to create a mirror of either a single volume or a trio of volumes. So imagine a situation like in an experiment when you have two end caps which are exactly the same. And so you don't want to implement the two. You can make a reflection of one end cap to the other according to an axis. So this is possible. So one thing that you have to consider is that when you do a mirror of symmetric volumes, it is not a simple, the operation that you do is not a simple transformation or 180-degree rotation. It is more, in the sense that the reflection is a real transformation by its own. So you see, if you do a translation or you rotate them, it won't be the same as the original one, okay? So a reflection is a special transformation that should be applied to the geometrical shape that is concerned. So in G4 there is a special shape for this, which is called G4 reflected solid. It's a class which is inherited from G4V solid, which is the class that represents all solids in G4. And it is an utility essentially that is used for representing a solid that is shifted from its original reference frame into a new mirror-symmetric one. And the reflection, which is a G4 reflect 3D, is then applied as a decomposition into rotation and translation. And for using this utility class, there is a factory, G4 reflection factory, which is a singleton object that uses reflected solid for generating placements of the reflected volumes. So this is the main method of the reflection factory, which is place. This method essentially allows you to take a logical volume and a mother volume, a transformation and a name to return you a pair, which is the physical volume, and the second is a placement in the reflected manner. And this function will, based on what is the logical volume that you pass to it, it will do automatically the reflection of all daughters of that logical volume. So if that logical volume is a subtree of volumes, it will automatically apply the reflection to all daughters of that tree. Okay. Independently if it is a placement or a replica. So if it is if there are replicas inside that tree, it will make the reflectioners of the replica automatically. The other is the replicate, which is similar to the other one, but it applies to replicas. So in that case, you pass as logical volume the one that contains the replica and does the replication. But in general, you don't need to call this. Just the first one is important because it will apply this automatically in case a replica is part of your hierarchy. Okay, so that's, I think, is all I wanted to touch today. So tomorrow, I think on Wednesday we will go through other concepts like the concept of regions that you see is very important. We will talk about geometry optimization, so we will see how the optimization structure is created when you create your geometry. We will see how to define geometry in parallel, so that may be then tracked in parallel. How to specify geometry that can move, so when you have parts that move inside. We can see how to import CAD drawings, what is the different ways to do that. And then finally, we will go through some tips and methods that will be useful for you to know, and also for implementing at the best your geometry. So that's it for today. Any questions?
Okay, I don't see any questions in the room. Let me double check again on Mattermost. I think we've exhausted the questions on Mattermost for the moment. So